All right, this is our last section for which we're going to be talking about logarithmic and exponential equations. And today we're actually trying to take the properties that we learned in the last two classes, the properties of logarithms and exponents, and use those to solve some equations. Some more general rules, right? Some more general rules is that if we can get the bases of an exponential or the base of a logarithm to match up, then the two arguments must be equal. So for example here, if I had 3 to the x, let's get my pen here. If I had 3 to the x equals 3 to the y, that must mean that x equals y. That's what this equivalency property is meaning. As long as the base is the same, then the exponents must also be the same. So in some problems, if we can get the base to be the same, then we can use that property, right? So here, any exponential problem, any exponential equation that I look at, the first thing I'm going to try and do, the first step, is to try and get the bases to match up. So this one has a base 3. There's no way to reduce that at all, but can I write this as a base 3? And so in my calculator, I'm just going to start trying 3 to the 3. Nope, that's 27. 3 to the 4. Oh, what do you know it? 3 to the 4 is 81. So I can rewrite this as 3 to the 2x minus 6 equals 3 to the 4, right? So the first thing I'm going to try with an exponential equation is to try and rewrite it with like bases. Now, if they have the same base, then I can apply this rule. That means that 2x minus 6 must equal 4. And now I can solve this just like a linear equation. 2x equals 10, x equals 5. And we can always go back and check our answer, right? So if I check my answer here, 3 to the 2 times 5 minus 6, that's the same thing as 3 to the 10 minus 6. That's the same thing as 3 to the 4. That's the same thing as 81. And so look, the left side of my equation does equal the right side of my equation. X equals 5 is our answer. Here's a couple more of these. Remember that anytime you have a fractional exponent, that's the same thing, a fraction, that's the same thing as a negative exponent. So if I rewrote this, I'm seeing a lot of 5 stuff here. I know 5 squared is 25, right? So the hard part's going to be getting the fraction to match up. 25 is the same thing as 5 to the 2 to the 4 minus t. 1/5 is the same thing as 5 to the negative 1 to the 3t plus 1. And now I can multiply my exponents that are there, right? I do have to distribute, so that's the same thing as 5 to the 8 minus 2t equals 5 to the negative 3t minus 1. And since the bases match up here, the exponents must equal. 8 minus 2t equals negative 3t minus 1. I can solve this again. It's just a simple two-step linear equation. That'd be t equals negative 1. I can subtract the 8 and get t equals negative 9. And again, we could go back and sub that in up top and make sure that our answers actually did work out here. I'm confident that it should. Take a second and try to solve this next one. I'm going to give you just a couple of seconds before I unfreeze it. Try and get like bases. I like to say there's more than one way to skin a cat. On this one, you could use base 2 or you could use base 4. So I could write the left side as 2 to the 2 and the right side as 2 to the 6, I believe. Let's check that. 2 to the 6 is 64, yep. Or I could write it as 4 and 4 to the 3. It looks like the method I chose was 4 and 4 to the 3. Here, I'll work it the other way for you. If I had 2 squared times 2x minus to the 2x minus 3 equals 2 to the 6, I would end up with 4x minus 6 equals 6. Add the 6. 4x equals 12, so then x equals 3. What do you know it? We got the same answer either way. So the first step for an exponential equation is check and see if you can get the bases to match up. If you can, you're in a good spot. If you cannot get the bases to match up, so in this example, for example, we want to get the same base. 7 to the nothing equals 60. 7 squared is 49. 7 to the third is 343, so we just skip over it, right? And so what we can do instead is use our properties of logarithms to try and solve this. I want to get the x out of the exponent, and so I'm going to use the property of logarithms that log base b of b to the x is equal to x, right? If I can get the base of the exponent and the base of the logarithm to match up, then the exponent will fall out. On this equation, for example, I have to do this, it's the same thing. I have to keep my equation balanced. If I do anything on one side, I have to do it on the other side as well. So if I do log base 7 on both sides, This is a trick that you just have to memorize, right? You just have to learn the trick. If we can get the base of the exponent and the base of the logarithm to match up, then on the left side, look at this rule, and look at what I have on the left side. I'll just have x equals log base 7 of 60, and I'm going to stop right there. We could type that in our calculator if it asked us to let's see, if it asked us to evaluate it right, if it asked us to actually evaluate or write it as common logs or write it as natural logs, if I wanted to type it in my calculator, I could type it as log 60 over log 7 and get a decimal point. I'm just going to leave my answer just like this. That answer is going to be perfectly fine in MyLab and in Alex. Here's another example. What we could do first is maybe subtract the 820. If you read the steps up here, it says first isolate the exponential expression. So here, this subtracting the 820 is going to help me to isolate that expression. 49,600 minus 820 gives me 48,780 on the right, 10 to the 5 plus 2x. All right, let's use that trick here. Let's use the trick. We want to get that out of the exponent. So what we can do is apply a log with the same base on both sides. If you do it on the left, you have to do it on the right. On the left side, we're just left with 5 plus 2x. The log with a base and exponent with a base match up. On the right side, that's not going to be a nice number, so I'm going to leave it. If I wanted to type it in my calculator and get an estimated value here, I could, but I'm going to leave it. Subtract the 5, so we want to get x by itself, right? We really want to get x by itself. If we subtract the 5, that's one step closer. Log base 10, 48,780 minus 5, right? We can't combine those. They're not like terms. They're not alike. The 5 is not inside of a logarithm. We can't combine them. The last thing we can do is divide both sides by 2. And so x equals, I'm going to have this big expression over 2. Log base 10 of 48,780 minus 5. That is my final answer right there. It does not look nice, but that's it. Again, if we wanted to get an estimated value, we could type it in the calculator and get a decimal. That answer is going to be fine in Alex, and that answer is going to be fine in MyLab. Take a second to try and solve each of these. On this first one, I would start by dividing by 18,000 to try and get the exponential equation by itself. Then we can apply the same base on both sides. So I would try log base e. That's the same thing as ln. And then we could solve for t. And here, I could leave my answer just like this. I could leave the answer just like this. That's perfectly fine. Or I could type it in the calculator. All right, on the next example, the same thing. I would start by subtracting the 400 to try and get the exponential by itself. Then do a log with the same base on both sides, log base 10. That's the same thing as just a regular log, common log, right? Subtract the 1, divide by the 4, and that's our answer. Again, we could type in the calculator or we could leave it just like that. I could have on this side, notice I had the 10 left in my answer. I could have left that 10 off. A log base 10 is the same thing as just regular log with no base. Remember, with no base, that base is understood. That base is understood to be 10 if I don't write it in. All right, this is the toughest one on the entire slideshow. This is the toughest one of the unit probably. If we have ones with bases that don't match up, right, there's no way to get the bases to match up. That's always our first method of defense. Can we get the 4 and the 5 to have the same base? Nope, can't do it. I could take a log on both sides with the same base, right? So I could do log base 4 and that will handle the left. Or I could do log base 5 and that would handle the right. But it's not going to handle both. And so what we're going to do here, this is going to be a pretty lengthy process. What I'm going to do, I could do is a common log or a natural log. I just like to, my handwriting turns out better if I use a natural log. So this math trick, this is another trick in your bag of tricks. I'm going to apply ln on both sides, 4 to the 2x minus 7. ln 5 to the 3x plus 1. I just applied a ln to both sides, right? I did the same thing on both sides. As long as I keep it balanced, it's legal. Now, we have the exponent rule from a couple of, actually that was last lesson, the properties of logarithms lesson. If you need to go review that, do so. But your exponent can actually come out front. With any logarithm, you can bring the exponent out front. So 2x minus 7 ln 4 equals 3x plus 1 ln 5. The exponent comes out front. Let's go ahead and distribute now. That would be 2x ln 4 minus 7 ln 4 equals 3x ln 5 plus 1 ln 5. And now we're going to use this handy trick that we keep coming back to, and that's factoring, right? If we can get all the x's on one side, so subtract the 3x ln 5, and all the numbers on the other side, so add the 7 ln 4. Nothing here is a like term. So there's no way I can actually combine these things, but I can write it as 2x ln 4 minus 3x ln 5 equals ln 5, that's that 1 ln 5, plus 7 ln 4. All right, here's my handy trick. Once we have the x's to one side, we can factor an x out, and I'll have 2 ln 4 minus 3 ln 5. I factored it out as a GCF. I'm going to leave everything else exactly the same. And then since I have x, one x over here now, right? So I had two x's. I had an x here and here. I'm working. I finally am to a point where I only have a single x in the problem. I can divide both sides by 2 ln 4 minus 3 ln 5. Divide both sides. And we're going to have just x. I told you this was a tough problem. This is a really tough problem. You can watch this as many times as you need to until you get the hang of this. But the trick is getting all of your x's to one side, and that way you can factor an x out as a GCF. Here's another one that's just the same way. Take a second and see if you can follow the same exact steps to get your answer. It doesn't matter what base you use. I should have said that on the last problem. You could use log base 10, log base 3, log base 2. It doesn't matter which base you choose to begin with. Just pick one and stick with it. I choose ln almost every time because my handwriting stays a little bit better when I use ln versus log. Distribute. Try and get the x's to one side, numbers to the other side. Factor out your x. Divide both sides. The answer doesn't look great, but that is the answer. It is an actual answer, right? We have an answer we could type in the box, and that is the correct answer that Alex or MyLab wants. All right, sometimes we do have exponentials in quadratic form. This is a little bit more rare, but if we look at this as, this is almost like x squared plus 5x minus 36 equals 0, right? It's very close to that. It's in the same form as that, in fact. It's in the same form. So what if I use star method to factor this with negative 36 on top, a 5 on bottom, a 1 and a 1, and instead of an x, right, I just have that instead of an x. So e to the x, e to the x. Can I multiply to negative 36 and add to 5? It turns out positive 9 and negative 4 will work here, right? So I should have e to the x plus 9, e to the x minus 4 equals 0. For any quadratic, the steps are get it equal to 0, factor it, and then set the factors equal to 0. Right? For every quadratic, those are the steps. As long as factoring works, right? And if factoring doesn't work, then we go back to a quadratic formula. But here, we've got it equal to 0, right? Step 1 was already done for us. Step 2, we factored it, check. Step 3, we need to set those factors equal to 0. So e to the x plus 9 equals 0. E to the x minus 4 equals 0. And now I can just go through and solve. I'm going to sort of solve both of these in tandem here. E to the x equals negative 9. E to the x, e to the x equals 4. And if I want to get x by itself, remember, to get it out of the exponent, I need to do a log base e on both sides. That means ln. And then I'll have just x equals ln negative 9. Just x equals ln 4. And if you type these in the calculator, you'll notice that ln of -9, this is actually not a real thing. When you type it in, you get a domain error. And so that is not in our included solution set, okay? Anytime you have to take a log or an ln of a negative number, it's not going to be included in your solution set. So this is our only solution here. If you went and subbed that back into the equation, I know it looks wild, but it would check out. All right, the inverse of that rule, right? We can do the same thing with logarithms. If we have log of a base with log of the same base, see this, the b and the b. If the bases are the same, then x must equal y. You see that? This is our equivalency rule. And notice here that our bases are the same, log 2, log 2. If our bases are the same, then the arguments must be the same as well. 3x minus 4 equals x plus 2. And then we can solve this just like a regular two-step linear equation. Add 4, that would be 2x equals 2, x equals 1. You should go back and check your answers. Always check your answers on these, okay? You should always go back and check your answers. I'll say it one more time. In a logarithmic equation, you should always go back and check your answers. If I was to sub that back in, I would get a domain error. And so on this problem, I actually have no solution. For every logarithmic equation, you should check your answers. Remember, the way that I would type this in the calculator is I would say log 3x minus 4 over log 2. So in the calculator again, remember our calculator, it just doesn't have a log base 2 button. It doesn't have a log base 2 button, so we have to use that change of base rule to check it. So that'd be in the calculator. Log 3 times 1 minus 4 divided by log 2. That's exactly what I'm going to type in my calculator right there, and it gives me a domain error. All right, solving another one. Okay, that equivalency rule, notice that there's one logarithm on each side. This does not work unless there's one logarithm on each side. One log on each side. Now, on this one, we have more than one logarithm on each side, right? And so what we're going to have to do is use those properties of logarithms that we had in the very last lesson to combine them. We only have one on the left side. That's great. On the right side, this is the quotient rule, where if I have subtraction, that's the same thing as combining it and make it x plus 6 over x, right? That's that quotient rule. Now I only have one logarithm on each side, and notice that they both have the understood base e. Since they both have the same base, then my arguments must be the same. I shouldn't have said equals there, I'm sorry. X minus 4 equals x plus 6 over x. I'm going to go on and make a note over here that x can't equal 0, right? Because if x is 0, I have a problem. All right, I'm going to multiply both sides by x. So then I have x squared minus 4x equals x plus 6, right? On the right side, those x's divide away. I'm going to get everything to one side. This looks like a quadratic, so I'm going to follow the same 3 steps I followed a minute ago. X squared minus 5x minus 6 equals 0. So get it equal to 0, factor it, and set each factor equal to 0. I get positive 3 and positive 2. I really want to check both of those answers. Doggone it. I really think that neither of those answers is going to work. Oh, wait. I didn't factor it correctly. I got in a rush here. This should actually be x minus 6 and x plus 1. I'm doing star method there to get those numbers. I'm just trying to do it in my head and speed this up so the video isn't too long. So my solutions here are actually x equals 6 and negative 1. Again, logarithmic equation, always check your answers. Always check them. The negative 1 is going to give you a domain error. If I sub ln negative 1 minus 4, if I type that in the calculator, it gives you a domain error. X equals 6 is the only solution that works here. We're on slide 12 of 15. We're getting close. Okay, solving logarithmic equations. If you're given a logarithmic equation, again, you're going to try and get the logarithm by itself, and then we're going to rewrite it as an exponent a lot of times, right? If we rewrite it as an exponent, it's going to help us out because that helps us to get the argument out of the logarithm. So first thing I'm going to do is divide by the 4, right? I want the logarithm to be by itself. So that'd be log base 3, 2x minus 7 equals 2. And now, remember this form. If I had a to the x equals y, that's the same thing as log base a of y equals x. I'm just going to go this way. I'm going to go to the left, right? I have something written as a logarithm. If I want to write this as an exponent, I would have 3 to the 2 equals 2x minus 7. 3 to the 2, I know that's 9. I can add 7. I can divide by 2 and get x equals 8. And I want to check that. Obviously, I want to check that answer and make sure that it works. In this case, it does work. So the steps here. Get the logarithm by itself, swap it out to make it into exponential form, and then try and solve it, right? Your exponential form should just give you a number. Try this one. Notice it's just a regular common log. That means it's base 10, right? The logarithm is already on a side by itself, so I can write it as 10 to the 2.6 equals w plus 47. Subtract the 47 from both sides. We get something like this, and that's probably a fine answer. But if I wanted to type in the calculator just to get a number, that would be the number. All right, let's see what we can do here. What can we do? What can we do? We have logarithms on both sides, but this thing is not in a logarithm, and it's not combinable. So why don't we try to get all of the logs on one side? So I'll just add that to both sides. So then on the left, I'll have log base 2 of x plus log base 2 of x minus 2 equals 3. Now I can use the product rule, right? The product rule says any addition in separate logs can become multiplication in a single log. That's the same thing if I simplify it as x squared minus 2x. That's a square there. Here, let me grab my eraser. I'm trying to go a little too fast here. I just distributed that x in. All right, now I have one log on one side, just a number on the other side. If I rewrite it as an exponential, that's the same thing as 2 to the 3 equals x squared minus 2x. 2 to the third is just 8. And then I can subtract the 8 from both sides. This looks quadratic, right? Anytime I have an x squared, I'm seeing a quadratic form. That means that 0 equals x squared minus 2x minus 8. And I'm, with a quadratic, always get it equal to 0, factor it, and then set the factors equal to 0. Since we started off with a logarithmic equation, we really want to check our answers and make sure that they work. And if you're seeing a trend here, you're probably thinking that the negative 2 is not going to work, and you would be right. The positive 4 is going to work as an answer. The negative 2 is not going to work. So positive 4 is going to be our answer. Nice work. And next class, we're going to move on to a whole different topic. We're going to talk about solving systems of equations next class, and then try and move on to solving systems of inequalities. If you've made it this far through logarithms, a lot of people either love them or hate them. You either start off with people that are very strong in math. They typically don't like logarithms for some reason. People that are weak in math, they see the trends here a little bit better.